Welcome again. We'll be talking about practical considerations when it comes to finite elements. So there's various errors that people make when you do analysis in finite elements. Typically there's various sources of errors. I'll start first with user errors. So a lot of the times there's mistakes made in the software. You'll use the wrong element type. You'll have a bad mesh used. For example, here there's a fillet, and here you can see that there's a single element across the fillet. If I want to get stresses in this fillet, that's not a great mesh. In fact, here you can see only a few elements, and you're not representing that curvature very well. So one thing you could do is use closed form solutions, use a far field stress here and here to get your better solution using the handbook. Otherwise, you may want to refine the mesh in that area. As you know, linear triangle elements can also be a problem. In these cases, you also want to pay attention to make sure that you're representing a stress field correctly. If this is an area of no concern, then perhaps it's fine, because maybe you're focused on a different area of the structure. But as you know, we've shown you that triangular elements can result in locking. You may have seen that in your homework. And so for that reason, you also want to be careful. I always look for typos. Units have been a big issue in my area of expertise. Typically, if you're given a model, make sure you know what units you're working on: inches, pounds, millimeters. Be consistent with the units, metric versus SI. Other areas of problems I have seen is could include boundary condition errors, loads not applied properly. You thought you included all the loads, but you didn't. So always check your results, compare, refine your mesh, do a lot of different checks. So for example, other errors I've seen, this is from a paper I wrote. If you're interested, I'll email it to you. Failure modes are not evaluated adequately. So you're looking at, for example, a brittle material. I'd rather you look at max principle, because max principle is very failure criteria for brittle materials. Metals, you may want to use von Mises, but also check max principle, and so forth. I've also seen composites not represented correctly, so the ply angles may not be specified accurately, or the material properties could be incorrect or assumed instead of measured. And so sometimes when you put the data into your model, is done incorrectly. Also, making sure that your composite properties match up the orientations of that ply. Okay. Mass definition has been incorrect or different units. The geometry does not compare well with CAD. It just looks different, and so that can be a problem. Incorrect stiffness. So if you have a joint, a bolted joint, I'll show you an example. Perhaps the joint representation is not very good, or is not adequately representing the behavior of that joint. Using a coarse mesh in an area where you have stress risers, stress concentrations. A coarse mesh is not going to be able to pick up the stress concentration very well. So you may want to refine the mesh in that area, or use Hancocks if you have this far field stress. Here are some examples of problems. So the drawings, in one example, the material was all along this edge in the drawing, but in the actual model it was only represented as a section of that. That's an example of something I've seen. For example, in the drawing, the cutout is here, but in actuality the model has it shifted up, forward, up. We've seen problems also with how the connections are modeled. In the drawing, there's no clips or some amount of support for the joints, yet the model has some clips being modeled. So that's not representative of the reality. On other issues, you may not be able to see these very well, but here's some other examples where instead of using a beam element, it should have been represented like a solid element instead. Here, other examples, you have a tube. So that's a thin shell, so that makes sense. But then this one here is a solid, some sort of solid component, well, that was represented as a beam. That does not look like a beam to me. And so that's going to give you incorrect representation. It's better to model with solid elements there. Here, this base may look like a plate. Sure, it looks like a plate, but the aspect ratio is not such that this dimension is thinner than the others. So therefore, we got to be careful. And in this case, I will have represented this as solid elements, as an example. Yeah, and then this is not a beam, right? This looks more like a plate, but that was represented as a beam here. And so be careful how you're representing things. They need to be representing reality. Remember, you're trying to idealize the physical structure with elements. And so you want those elements to accurately represent or model this physical structure. Okay. Other problems I've seen is, this comes from the same paper, but you have a beam to plate geometry, so that's a connection right there. And so sometimes what you may want to do is constrain with the rigid bars, so 1D elements. Just make sure that beam, its footprint is connected well to the shell plate through rigid elements encompassing the footprint of that cross-section. Otherwise, you'll have too soft of a behavior of how that beam moves relative to that shell. A 2D cross-section of that will be this plate coming in. So you want to have rigid body, rigid elements, 1D elements connecting to that footprint well. So you have a good connection between that plate and this plate. Here's from a paper that look at different kinds of joints. And in here, instead of having solid elements, because that would be computationally expensive to model every bolt with solid elements, one representation is to have a beam, and that beam connects the surrounding hole with distributed coupling, RB3s or RB2s in Nastran. And here, there's other ways that they looked at in this paper, so I recommend you look at that. But there's plenty of papers in this area. Another approach is to convert the solid elements, these plates, abutments, into shell elements. If they're long enough, so they're thin in this direction, but long in the other directions, then in that case, you can represent this as shells, and then use a beam to connect the two shells together using a distributed coupling on the shell, and then beam elements represented in the bolt. Important to recognize that that might not be an accurate representation. So making sure that that joint behavior matches physical reality will be a good thing. And you can do that through testing or building some more detailed models and ensuring that the stiffnesses are, or this joint stiffnesses are represented well. Okay. Other errors that we've seen is people having very few elements around the hole. But if it's a critical area, at least 12 elements should be used around the hole. Other issues like this one I discussed, you could have a fillet, but then representing that with no elements to sort of represent that fillet. So if it's in a general area of no concern, not an issue. But an area of concern or an area that you want to explore carefully, just put more elements and get about 3 elements around that fillet. Other things to point out, so these, for example, a joint, a clamp, and these are connected by spot welds. You can represent the spot welds with rigid elements, typically, and then these two structures look like shells or plates, so you can represent them using the mid-surface of these plates. So that would be a good way of doing it. If you have a fillet weld, some people will represent that with a single row of shell elements. Again, you won't trust the stresses here in the fillet, in the weld, but you can get the stresses in a far field and then correlate the failure of that sample with testing. So just do a subscale test of that fillet, or try to find a way of correlating this to more realistic behaviors, through testing or more detailed analysis. Does that make sense? Everybody follows? Excellent. So if you have a 3D body given to you, 3D solid, and it looks like you can represent it with shell elements or plate elements, you can extract the mid-surface. So here's the mid-surface of that 3D body. And then just make sure your mid-surface follows very well and that you don't have some disconnections in here, because when you mesh it, you want to make sure you're representing the thickness of all these areas accurately. So for example, if the thickness is varying, right, you want to keep track of that, because then the shell elements here, you'll have to specify thicker or thinner depending upon how the thickness varies, right? We know that the thickness is an important parameter for the shell elements. And so you want to make sure you're doing that correctly, applying those properties, those section properties accurately in the models, okay? Any questions? No? Typical model check. So when you get a model or you're constructing a model, make sure that the dimensions match well the CAD geometry that applies, match up the drawings. Make sure you have material properties in the model that make sense, that they actually match some sort of test database or material database. Make sure you account for temperature dependence on the material properties. So if you have an aluminum at hot temperatures or cold temperatures, make sure you have the correct mechanical properties for your application. Mass properties, make sure your boundary conditions are good. Check that there's no free edges that could represent cracks or coincident nodes that should not be. If you have coincident nodes, most likely you have cracks in that area of the model, so you have to go and check that. Check the surface normals of the model to make sure they're pointed in the same direction. One thing that's very useful actually is to take a model once you're done, apply a gravity load. Just apply like 100 Gs. Exaggerate the plots and then see if there's anything disconnected or acting weird. That has been helpful to me. Do element quality checks. I'll talk about that in a few minutes. And then make sure if you have shell definitions, they're defined properly. And just make sure that whatever element type you're using, whether it's a beam, shell, solids, that they're an adequate representation of physical reality. And then do rigid body checks. That's a good thing to do as well. And make sure that any simplifications you make, say there's cutouts in the structure that you don't want to model, make sure that just delete a couple elements in the area and see if it changes the load distribution. You don't have to make it perfect. So if you think a cutout doesn't really matter, and it's circular, and you don't want to mesh that because you don't think it's going to matter, just remove a couple elements in the area, rerun the model, and see if it matters, right? Because maybe that's not the area of concern in your model, right? So important things to keep in mind. Other issues are duplicate nodes, like I mentioned before, in HyperMesh, for example, is what the software I use typically. You can actually find them quickly. So here is showing up as 3 nodes being highlighted. Duplicate elements is another one I've encountered myself actually. I create a mesh and I duplicated some elements because I wanted to translate or do a few things with them, and I forgot to delete those duplicate elements. Well, those duplicate elements may not give you an error. Everything may run fine, but these duplicate elements can actually give you additional stiffness to the structure, and you may not be aware of it. So that's a big one I've encountered myself. The mesh not matching the geometry well, we talked about that, and disconnected elements, so they'll create a crack. So sources of error can also include including elements that are not of high quality. We'll talk a little more in detail about this, but elements are highly distorted. We'll have a Jacobian that is not well defined or is ill defined, and so the more distortion you have in a Jacobian element or in an element, the Jacobian will be of a value that's not very good for structural analysis. And so here in HyperMesh, for example, it will give you, you can click any of these buttons and it will show you, okay, this Jacobian for this set of elements, and it will highlight them for you, has a Jacobian of 0.7. Well, a 0.7 is good, But if it's anything less than 0.7, then it's going to highlight them for you, and you may want to revisit those elements a little bit more. Okay. Aspect ratios can be a problem. So if the aspect ratio is such that usually 1 to 100 or 1 to 50, depending upon the code, then the element will not behave very well, and you're going to get some results that may not make much sense. Anyway, here's the other checks. There's aspect ratio, skew, cell squish, length, and there's other ones you can check, and I discussed some of them here visually. So one way to determine whether an element is a good element or not, you can visually check it as well, or you can look at a definition I'll give you very soon. But if I took this square, for example, for me this is a good element because it compares very well to the standard isoparametric element. While these elements, they don't look great, they could be okay. But if I were to use a isoparametric formulation, I have to turn this highly distorted element into a square, so the Jacobian may not be very good for that element. Okay, and then these ones are great, but then this one has aspect ratios that are not very good. So how do I know more qualitatively if that element is good or not? So one thing to do is that if you have, for example, I have a square element, and I draw a circle in the inside of that element, and I draw a circle to the outside of that element, right? So in this case, the ratio of this radius is quite small. So if you take the radius of the outer circle to the inner circle, that's quite small. But now if I have a highly distorted element like this one here, and I draw a circle in the inside and a circle in the outside, you can see the ratio of the radius of the circle in the outside compared to the one inscribed into that rectangle is pretty large. So keep this ratio small, and then that's going to basically tell you that the element is of better quality. A triangular element that's highly distorted will look like that. So clearly this is not a good element. Some cases you have no choices, and so you may have bad elements and you can't do much about it. In those cases, you want to use stress fields. Far field stresses to write your calculations. You will use hand calculations based on stress works table, like a book, handbook of formulas, Bruns, or there's various books out there. Peterson's stress concentration book will have a bunch of them where you can do hand calculations. You'll take the stress field and then you apply closed form solutions. That's sometimes a better choice than trying to refine the model. Other users' errors are, I think I discussed these ones. Loads can be misapplied in boundary conditions. Numerical errors are a possibility. Nowadays, it's less of a problem. Most computers, they're double precision, but single precision also. But this won't be a big problem in a lot of our issues, in a lot of our problems. Discretization error, so I think I discussed this quite a bit maybe a couple of lectures ago, but I do want to emphasize it. So there's two ways to refine your analysis. One way is to do P-refinement, which is to use a higher order interpolation function for your elements. So instead of linear elements, you will use quadratic elements. H-refinement is basically you're taking your elements and meshing it with smaller element sizes. And so that's one way to do it. Brute force, just refine the whole thing without thinking about it. But that may be computationally expensive. So what you may want to do is to refine in areas where there's large stress gradients. For example, if the stresses are very large here and the gradients are not very large, you don't have to refine it there. Just because the stress is high there doesn't mean you have to refine it there, because maybe the stresses are not varying significantly from element to element. But the minute that the stresses vary significantly, and that's an area of high concern, you may want to refine the mesh to the point where you're capturing that stress gradient. A good rule of thumb is to make sure that about 2 to 3 elements have about the same stress level. Okay, so if I have an element here that's about, I'll show you an example, I think, coming up. So, for example, here, clearly this element has a completely different stress from these elements. And so, therefore, you definitely want to refine a mesh to the point that you have multiple elements that are in the same color, right? Same, basically within 10%. And so if you can do that, you basically have a nice mesh, a converged mesh. In some cases, the stress, for example, in this case, is a hole with a load applied, far field. In this case, you know, we're in good shape because this stress concentration did not change very much as I increase the mesh density. So sometimes doing these studies are very useful because it may tell you what level of refinement you actually need. The reason for that is because there may not be a good payoff. I may have, with small number of elements, I may be able to get to the solution. And if you have large number of elements, that's going to increase the computational time, and you don't have a huge payoff. It's going from 4.52 with 20,000 elements, and only with 100 elements, I can probably be about 4.48. That's not a big difference, right, between 4.5 and 4.48. So, in general, my suggestion is to do some sensitivity studies and kind of gauge what kind of element size you need. One thing to point out is the error. So I want to point out a few things. The error typically is proportional for displacements. Is proportional to the characteristics length to the p plus 1. And so if I increase the order of interpolation, so p is a polynomial, so if I have a linear element, this p will be 1. If it's quadratic, p will be 2. You can see as I increase p, if h is less than 1, then you expect this error to decrease. Do you agree? Can you see that? Another thing is that if I decrease h, then I also decrease the error. And so I'm able to do that. But if I take derivatives of this, say I take a first derivative of that, second derivative, third derivative, now the error is proportional to h to the p plus 1 minus r. And you can see here that even if I increase the order of interpolation, that the derivative is not going to converge as quick, or the error will not decrease as quick as it does for the displacements. As an example, let's take a Q4 element. A Q4 element, the error, so it's a linear, you agree it's a linear interpolation? Yes? So P is 1, so the error for displacement is proportional to h squared. So if I keep the element size, if I decrease the element size, then the error will decrease proportional to h squared. But now when I look at strain, we know that strain is the derivative of displacement. So therefore the error will be proportional to h. And so if I decrease the element size, here you can see clearly that the error is not decreasing at the same rate as it does for the displacement. Does that make sense? So displacements will typically be converge a little bit quicker than the stresses. Keep that in mind. So let's talk about quadrature error now. So quadrature error, if you have distorted elements like this node, we discussed this. If this node is not in the midpoint between on this edge, then in that case you will have undistorted or distorted element. This is actually a distorted element. No, I'm sorry. This is placed in the middle. So this is an undistorted element. But if it's placed away from the midpoint, then it will be a distorted element. And so the Jacobian will be a rational, irrational, or a fraction. And so it's not going to be an exact integration scheme. It's going to be approximate. Other cases are, for example, a quadrilateral here is distorted because the angles are not 90 degrees. In a second order quadrilateral, the midpoints are not in the center, the midpoints of the edges. So in that case, that also can give you a Jacobian that's not exact, will be approximate when you use quadrature rules. Another point I want to make is that if the edges are not straight, that's also going to give you a Jacobian that's approximate when you do the Gaussian quadrature, the integration schemes. Okay, are you guys following? Yes? So in these cases, you will have some error in the Jacobian calculation. Okay. Now, if this is a square, right, a perfect square, then the Jacobian will be a constant value, and you'll be able to integrate that fairly well. Okay. I believe a rectangular element will also be okay. Okay. So there are various integration schemes that can be used. Full integration. I don't know if you recall, but for the Timoshenko beam, we did full integration, and remember what happened to those elements? It locked. We had shear locking, and then we found that we had to use less accurate integration point. Basically less accurate or less number of integration points to integrate the stiffness matrix, and we found we actually improved the solution doing that. So full integration, for the most part, in almost all cases, is going to be the proper solution to a lot of our problems. Be careful, because when you use Abaqus, Abaqus by default will usually default you to reduced integration right away. Like if you're going to use a brick element, I believe by default it will give you C3D8R. Well, that makes sense because it will save you computational time, and it's probably okay. But in a lot of our problems, that might not be okay. All right? And I'll discuss that. But point is that full integration for a linear element, just 1 point is enough. If you have a quadratic element, 2 points is enough. If you have a cubic element, 3 points is enough. Okay? But if you have highly distorted elements, now you may need more quadrature points. And so in those cases, using full integration may be the right thing to do. For Timoshenko, we saw that was a problem, and we did not get a very good result with full integration, if you recall that. And so also full integration is computationally expensive because I have to calculate all these integrals. I have to evaluate them at the integration point. So the more integration points I have, the more calculations I have to do. I think as you're experimenting, or as you may have experimented in this homework. I don't know if you experienced the pain. But, okay. Furthermore, for bilinear or linear quadrilateral elements, or bilinear quadrilateral elements, 1 point is enough. But if it's, again, distorted, then you may want to have more points, integration points. And then you also have for basically a higher order interpolation element, basically take a second order element, then you need 2 points or 4 points to evaluate that integral exactly. So that's full integration for 2D. And for 1D, I just discussed it. This was also discussed previously, just reminding you about this because I need to cover some topics here. Reduced integration. Reduced integration, we found for Timoshenko as an example that it actually improved the solution because the full integration was making the element behave fairly stiff, but by reducing the number of integration, we actually made it softer. We made it behave actually like the exact solution we found. So fewer points usually can be okay for undistorted elements, but can increase the error, right? So it can improve the solution for overly stiff elements like we found with Timoshenko beam. And Q4 elements also become locked if you have just a single row of elements. We saw that it became stiff. The solutions will become stiff. Using one reduced integration can help. The problem with reduced integration, however, while it sounds attractive, especially for dynamic problems where you're doing explicit time integration in Abaqus, or some of these time-intensive calculations, Abaqus will try to default to a reduced integration element. But the thing you need to pay attention to is the consequences of it. For example, if I use a quadratic interpolation with 1 point integration scheme, that's clearly a reduced integration, right? Because for quadratic interpolation, we need at least 2 points. But if I use 1 point instead, we found that when I evaluate, and we went over this, just a reminder, when I evaluate the stiffness, I get basically, I go through the calculations and I find that this row, which belongs to the middle node, has 0. So I have 0 stiffness. I have rigid body motion in that middle node. And so that's going to cause some numerical issues. Okay, so that is a problem. Okay. You guys follow? Let me explain some other issues you find with reduced integration. The issue is you can get spurious modes. I will discuss that in a few minutes. And we call this hourglassing. Sometimes you get singular matrices or zero energy. And the reason for that is because reduced quadrature can lead and fail to pick up deformations of the structure. Think about these Gaussian quadrature points as detection points inside that element. And so if those quadrature points are not picking up the deformation of the structure, you may have an issue. I'll discuss that in a few minutes with an example. We call this rank deficient when this happens, when it's not able to pick up the behavior of the deformation of the element. Zero energy motions, which may not be rigid body motions, are instabilities. We call them instabilities. And they can cause errors in the strain energy. You can also have, you usually don't have this issue with constant strain triangles, because constant strain triangle, by definition, gives you a constant stiffness matrix, regardless. You don't have to evaluate that with Gaussian quadrature, right? We found this through homeworks and our experiences here. Anyway, so let me cover some examples here on this. So let's take a quad 4. A quad 4 element. This is a very famous. I didn't put this together. This is in many different books. You have, if I calculated the eigenmodes of a stiffness matrix, right? So how many degrees of freedom I have in a Q4 element? 8. Thank you very much. That was quick. 8, right? So how many eigenmodes I expect for that problem for a single element? 8, right? 8, because I have 2 unknowns in each. Now we're not talking. Okay, so let me make sure you understand. These eigenmodes are not the buckling modes. These are not the mode shapes of a dynamic problem. This is simply plotting the eigenmodes of the stiffness matrix. Okay, calculating the eigenvalues and the eigenmodes of the stiffness matrix. So it's not a buckling problem or mode shape problem, dynamic problem. We're just looking simply at the eigenmodes of an element. And if I plot that, I get a rigid body motion along V. Makes sense. I should get a vertical motion. I get the axial motion of this element. That makes total sense. Or I have a rigid body rotation. Makes perfect sense. So these three can be suppressed, and you suppress that by prescribing boundary conditions to your model. So if your model is not properly fixed, you should try this in Abaqus. Don't fix your model and run it statically. You're going to have singularities. You're going to have a bunch of issues. So look at the dot message file. Take some of the models that we discussed in class. Don't fix it. And do a static calculation. You're going to see that the model is going to go haywire. It will give you some errors. But now let's look at a single integration point, reduced integration for a bilinear element. So if I'm an integration point down here, I'm a little ant in the middle of this quadrilateral, and I look that way, and I look that way, and I look that way, and I look that way. Do I see this moving outwards? I do, because I know I was here. This point can actually see that I was here and I moved here. I was here and I moved there. I can see I'm expanding. This element is expanding or contracting. Same here. If I'm this point here, this quadrature point here, I can also sense movement here. I can sense movement there. I can sense movement there. So a single quadrature point is going to pick up this behavior very well, which is basically stretching. It's picking this stretching very well. Now, if I'm a point here, okay, it's also going to see that I have shearing going on, because I see a change in angle there, change in angle there, change in angle there, and change in angle there. So that single point, quadrature point, can actually pick up deformations 4, 5, and 6 very well. But when I'm talking about bending, which is what 7 and 8 is going to come out to be, this is one of the modes you will get. If I'm this point here, tell me, can I sense movement there? No. Can I sense movement here? No. Can I sense movement there? No. Can I sense movement here? No. So what's going to happen, you're going to get something called an hourglass. That looks like an hourglass, right? And this is going to cause errors, okay, under bending conditions. That's why reduced integration for bending problems can be a problem sometimes, okay? And so now the behavior here is going to become singular, or it's going to become too soft. The behavior may not be as good, okay? And so now, if I were to look at in a mesh, you're going to get stuff like this. If I apply bending to this mesh, I'm going to get stuff that looks like this. Nonsense, basically. Here you can see that with reduced integration, with brick elements, you can see some nonsense here when I apply bending loads to this beam. You can try it at home. Just try it at home. Take C3D8R elements. By the way, C3D8R elements, I believe, is the default. So if I run an analysis and I apply a load, I'm going to get stuff that doesn't make any sense, okay? And some people don't look for these kind of things. They just run the models and just get the stress. They keep moving, okay? Your job is to be a police for finite elements, right? You should know better, okay? A full integration, however, did not suffer from these consequences. Now, I did not use C3D8 because C3D8 will behave stiff also. We discussed that. Even with full integration, C3D8 will become stiff, right? But if I now use reduced integration thinking I'll improve the solution, now I'm going to have a situation that's not the best either. So if now I use 20 node hex, everything matches very well, okay? And I can use 20 node hex with a regular mesh or a not very nice mesh. In both cases, very nice results, okay? Any questions on this so far? Excellent. Don't think that with second order elements you don't have problems, because you can have problems too. So with 4-point quadrature points, I want you to see with me, check with me, whether it's possible. And these are the modes. These are the modes for that, some of the modes, not all of them, for that element. And so if I look at few modes, if I'm an integration point about here, can I sense movement there? Can I sense movement there? No. Can I sense movement? No, you won't be able to sense movement, and it's going to cause this weird element deformation sometimes. And so you want to watch for that as well. These ones suffer from the same things too. Good news is that for second order elements, this behavior suppressed usually when you have adjacent elements. So if I have these elements and I have another element here and another element here, this mode is suppressed by adjacent elements, and this may not be an issue. But just keep your eyes open for it, okay? So another thing that people do to avoid an error, and Abaqus has this approach, is, as I showed you, reduced integration can result in a problem. And so what Abaqus does, or many of these codes do, they provide you something called Hourglass Control. It allows you to add stiffness that's artificial. It's made up to some level. And the idea of adding this artificial stiffness is to suppress the spurious modes that occur. Okay? And so by adding this artificial stiffness, you're able to mitigate these concerns. Abaqus uses a formulation from a paper from Belichko in 1981. He came up with this. And so you guys can read that paper if interested, or just read Abaqus. Will give you some guidance on how to deal with hourglass control. My suggestion to you guys is to stick to full integration if you want to not have to deal with a lot of these things, but then keep your eyes open for the issues that full integration can also give you. But the minute you go to reduced integration, look out for overly flexible behavior, things that don't make sense. That's why hand calculation is so important in everything we do. It's not just about running an FEA model, but also verifying your results. Okay? And here I explain some limitations of hourglass control that could be of importance.
So the only problem with full integration is that you might get shear lock, that's all?
Yeah, typically. For full integration, shear locking tends to be the problem. And then for reduced integration, the issues are zero energy modes or spurious oscillations in the stresses. That can be an issue. Okay? Excellent. Any questions? Any questions here?
Yeah, so let's say you run it and you do get shear locking, but you don't know it. If you wanted to confirm that easier, would you just increase the number of elements?
Yeah, absolutely. You want to do a mesh refinement study to look to see if you got shear locking. Another thing you can do is hand calculations. There's something simple you can always do. For example, I think somebody here ran, did you guys do problem number 2? From here. Yeah? Does it move at all?
Not much.
With triangular elements? I don't think this moves. You apply loading, it doesn't move. So if I was you, I'll run your model, right? Exaggerate the plot 10 times. And if nothing is moving, you know there's a problem. I mean, right? This one is locking, as an example. But that alone is not enough. You have to do some hand calcs to get some confidence. Or do some mesh refinement studies to gain confidence in what you're doing. Okay. Now, there's some tricks that exist in different finite element codes. It's called selective reduced integration. And so what you do here is, when I have a bending problem, you have no shear. So here, if I use a single integration point, we can call it rank sufficient because it's not going to matter for this problem. Although I'm not picking up the shear here or here. I'm picking some here and here, but it's not a problem for a bending problem, say. And then for bending, though, you do have a problem. We call this rank insufficient. So here, what you could do is do full integration for these strains, and then do reduced integration for the shear strain. And so now I'm selectively targeting the different strains differently. So what you do is you break up your stiffness matrix into 2. You agree that this plus this gives me a total stiffness matrix? Yeah? So what you can do is evaluate, remember the BDB matrix that we keep getting over and over? BDB, BDB. Almost every problem was BDB. If there's one thing you will be sleeping, I think for the next 50 years until you're no longer alive, is going to be BDB. That's the one thing you will remember from this class, BDB. And also, you remember the 10 steps in finite elements. All the steps, right? I don't think you will forget. And if you do, we have a problem. I'll retroactively not give you an A, okay? Okay, call me up when you forget this stuff. I'll make sure your transcript gets changed, right? We could do that. No, we can't do that. But if you're going to work in finite elements, you really need to keep yourself sharp in all this subject, right? But if this is what you're going to be doing, you don't want to get rusty. You want to go back and revisit some of the concepts here. But anyway, I can break up my stiffness matrix, right, into 2. And this one here, I will integrate fully, B, D, B, and I'll integrate this fully with full integration points, 4 integration points. And the shear term, the shear stiffness, I'll just integrate that with a single point. So that's called selective reduced integration. So to summarize, the sources of error typically tend to be user error, numerical error, modeling error, discretization error, and or quadrature error that's associated with the choice of integration scheme. Any questions so far? Okay. Let's go to the next topic, nonlinear finite elements. Why we don't hit that, and see how much we can cover there, okay? Let's do that. So for nonlinear finite elements, typically in a linear problem, the strains, actually the full strain Green-Lagrange strain tensor is 6 components that includes the higher order terms. But for the linear problem, these higher order terms are neglected. And this can be neglected when you have small displacements, small gradients, small rotations. And so in Abaqus, for example, if you turn in the step definition, star, step, comma, NLGeom, you make that null, it's going to use small strains, approximations. It makes sense if the strains are small, say it's 1%, so 0.01 times 0.01, what is that? 0.0001. It's really small compared to this strain. This is going to be dominating the strain value. So small strain makes sense if you're less than 1 to 2%. Another thing is if you're just looking at linear stress-strain relationships, so here's a stress-strain curve of metal, and I'm only in this regime, then it makes sense to just do a linear analysis. In that case, you're basically, it's a simpler analysis, right? Another thing you can do if the analysis, you think that, the stress-strain curve looks like this, but I want to run the model without having to do the nonlinear analysis, I could just run it linearly, and if the stress concentration at the hole, the stress concentration, the stresses are not higher than the ultimate, it's probably conservative. It's probably enough for you to stop there. But if now you have a stress that's 5 times the ultimate strength of the material, maybe you want to switch to stress-strain curve and use the full curve and do a nonlinear analysis, which is what this is here. So in a nonlinear problem, the strains can be very large, and you may want to consider them. For example, buckling is an example. So the problems you guys are working on, the buckling problem, that is a nonlinear problem because you're going to have high deformations in that wall that have to be considered. Material nonlinearity is another source of, so basically it's nonlinear stress-strain curve. Kinematic nonlinearity, where your boundary conditions are changing, that's a source of nonlinearity. Or follower loads. It's a small mistake, follower, so the load follows how the structure deforms. In this case, that's also a nonlinear problem that needs to be considered. Any questions on this? You guys understand the sources of nonlinearities? I'll give some examples.
Can you repeat that part that you're saying you have really high stress compared to
Yeah, if you run a linear analysis and there's a stress concentration in the model, say, if the stresses, if you can write positive margins for that structure with a linear analysis, you're probably going to be okay. But if the stresses give you a huge stress compared to the strength of the material, it may be worth doing a little more homework and studying, putting the nonlinear stress-strain curve and study how that stress concentration behaves, right? Because now you're going to properly account for the fact that there's plasticity at the hole and that the stress distributes much better at the hole than it will have with a linear analysis. So typical material properties include nonlinear elastic, plastic, hyperelastic, viscoelastic, viscoplastic. Abaqus has hyperelastic, has all these material models. Temperature-dependent thermal conductivity, I'll give you an example of that real quick. Geometric nonlinearity, so large deformations, large kinematic problems. Sorry, kinematic problems where there's large deformations, large rotations. Buckling analysis that you guys are doing right now. Boundary conditions where the contact is occurring, that's going to be a nonlinear problem because now the boundary condition depends on the geometry and the deformations of the parts. Or if you have a thermal problem where there's phase changes, that's going to be a very different problem as well. Here's an example of a 1D bar. I could take a nonlinear stress-strain curve, or I can include so normally we just include this, but for large deformations I can include this term. Okay, if I include this term and I include a stress-strain curve that looks like that, and none of these are linear, then my stiffness matrix is going to depend on the deflection. Normally, the stiffness matrix does not depend on deflection. You agree? Usually, when you calculate it for all your problems, was the stiffness matrix depending on deflection? No, it was a constant value. You inverted K, and you got the deflections, right? Is that what you did? Correct. And so now if the stiffness depends on the deflections, right? Now I have to solve this in a different way, okay? We'll cover a little bit about that coming up. Again, this is more of an advanced class, so I'll cover very, very top level. I'll teach you the fundamentals of the methods used in Abaqus to solve this, but I will not be able to teach you the more advanced nonlinear finite elements. I'll cover very top level. A contact problem, for example, when I take this ball and I apply a load against this rigid boundary, you expect this boundary to impart a load, a contact pressure on this ball that flattens that ball. And so in this case, the amount of load I impart also changes the amount of pressure that I'm applying and the amount of width. And so your boundary condition is changing clearly here. And so now again, the stiffness matrix depends on the deflection, which is what you're trying to solve for, so it's a nonlinear problem. Let's take an example of thermal conductivity. And radiation is actually a nonlinear problem as well. Because you have, in radiation, you have temperature to the fourth. I think the equation will have temperature to the fourth. That's a nonlinear problem. You have to use nonlinear solution techniques to solve that. But here is an easy one. Conductivity depends on temperature. So clearly here, when I go to my stiffness matrix, remember it's BdB, but in our case it's K because it's conductive. Capacitance is our stiffness matrix of heat transfer problems. You can see the boundary conditions also depend on this K. So K is a function of temperature. So here again, I can put it into this form where K depends on temperature, and temperature is what I'm trying to solve for. So it's a nonlinear problem. I cannot just invert this because I don't know K. K depends on T, and T is what I'm trying to solve for. Very nonlinear problem. Gotta find a way of solving that. In Abaqus, because I won't cover this in extensive detail, in Abaqus to activate nonlinearity, so for material nonlinearity, you'll put star plastic. So after star elastic, you give the modulus, the Poisson ratio. Star plastic will give you the opportunity to put in there the stress strain curve. And so you put the yield stress, and then you put the plastic strain here. And so you'll just number them all the way down. So you'll take the stress strain curve and put that in there. Make sure you are putting the correct, so say I go to a test lab and get the stress strain curve of the material. That data product that may be provided to you is an engineering stress, engineering strain. And depending upon the code, whether it's Abaqus or Nastran or ANSYS or all these different codes, they may ask you to put in there engineering stress versus engineering strain, or they may ask you to put the true stress versus true strain, and so you may have to convert it to those. Okay, just keep that in mind. And also, star plastic also has other options in Abaqus, such as isotropic hardening, kinematic hardening. You guys can go and look at those options for your. We won't have time to cover all the plasticity models that exist, but I do encourage you to go through the manual or take a plasticity book and learn about the different plastic material models that exist, plasticity models that exist. To activate nonlinear geometry, just make this equals to yes. I forgot the word yes, and this will activate large deflection theory as well. You have a question? Excellent. Here's an example. I want to show you this example. It's the simplest example I can think of to teach you nonlinear finite elements, or how, a little bit about how to solve this in a quick way. Okay, so pay attention here, and I think you'll follow it. Say I have a load that I apply of 16 pounds, but my modulus now depends on the deflection of this beam, of this bar, and the deflection, and the modulus depends on 20 u squared. So usually the modulus is constant, you agree? But I'm going to make it, I made it up. I made it up so that now the modulus is 20 times how much the deflection moves. So if the deflection is 1 inch, now the modulus is 20. If the deflection is ½ inch, then my modulus is now 5. So now it's dependent, and my modulus is now depending on the deflection of the structure. EA over L, so for A is 1, L is 10, E is 20 u squared. So if you calculate this, you get 2 u squared. Hopefully I did that math correctly. Check it for me. So the equilibrium equation for this problem is Ku equals F. K typically is AEA over L. In my case, it's 2 u squared. So I have u there, and then F is 16 pounds. So I have I have 2 u cubed equals 16. You agree? Yeah? if I put everything to one side of the equation, this is u cubed minus 8 equals 0. I'll call this the residual. Now, please do not confuse this residual with the residual function from weak form Galerkin. It's not the same thing. Okay? This is just the error you incur if I start and I say, okay, u is 0. Is that the correct solution? Are you here? Are you following anything I said? Yes? So if I put 0, I get an error of minus 8. That's not right. You know the solution is u equals 2. I just created an example that is probably not that realistic. The next example I have is much more realistic. But in this example, clearly not realistic. But I'll show you how to solve this nonlinear equation. Okay? Using even Excel. We can do this in Excel really quick. So to do that, we're going to use our favorite thing in the whole universe is Taylor series expansion. I'll show you how to do that. So I'm going to solve for you. And again, I can't tell Abaqus, hey, I have this huge number of nonlinear system of equations. Can you solve it exactly for me? It won't do that for you. We need to find a systematic approach, right? Because that's the whole point of finite of solving these nonlinear equations. So in this case, what you can do is use Taylor series expansion. Let's go to that. So RU, so what you do is, okay, RU plus DU. Let me check what RU plus U DU is. And so if I do a Taylor series expansion about U, I get this equals RU plus R, derivative of R respect to U, DU. You agree with this equation? Everybody agrees with this? What is my goal? What is my goal? I want this to be what?
0.
Yes, I want the future to be 0. I want this residual as I move forward in time to be 0. Because I want to get u cubed equals minus 8 equals 0. I want to get that u equals 2. So if I want to make that happen, I need to make that to 0, okay? And so if I go here, let me call u plus du equals the u new, the new value of displacement. And let me call u the old value of displacement. So that u old plus the change in u that I'm making is the new displacements, okay? So therefore, this is u new, this is u old, and these are u old. And this is delta u, okay? So if I want to make the future 0, you agree that this is 0 then? If I want to make it 0, I want to force it to 0? Yeah? You guys track? I'll continue here. So this is 0. So that's RU old, R prime U old du, okay? And so what I want to do is solve for du, and that's easy. I just solve for du right there, right? So just bring this to the other side of the equation, divided by R prime U old, and that's what I get. So now the prediction on how to improve, if I start with u equals 0, my u old is 0. That's not correct. 0 cubed minus 8 is minus 8. That's not giving me the right solution. So that's not right. If I put u equals 0, that's minus 8. That's not giving me the right solution. So for me to improve that solution, to correct it, I take this old value of u, okay, and I correct by du, and du is given by this equation, okay? And you saw how I derived that so quickly. All right, so let's see. For our case, what is RU old? No. General formula. Just give me the general formula. So R was u cubed minus 8. So what is RU old? U old cubed minus 8, right? What is R prime? 3 squared u old. Sorry, 3 u old squared, right? Sorry about that. Okay, so that's how you get to du. Okay, so let's see what we've done here. I did it here for you, actually. I did it here. And then what I did, I went to Excel, which is very visually appealing to me. So put u old here, right? I will start with the value of 6, just for the heck of it, right? We know that 6 is not correct, because 6 cubed minus 8 is way off from 0. That's not the right solution. I get RU old, which is 208, which is this equation here, is what I programmed there. U prime, R prime is this here, 3U squared. So I take 6, I put it there, and I do this calculation. And then I take this ratio here, and the minus of that gives me the change that I need to make. Right? So I need to make a change to U old of minus 1.92. So 6 minus 1.92 gives me 4.07. And now I'll use this new prediction of U, start over, and redo that. And you can see here quickly that about 4 or 5 iterations I get to a value of 2 for U. Okay, so I get the value of U, which is 2. Okay. Now, I don't know if you've noticed, have you run Abaqus and look at the message file? You should look at it. You should open the message file, and you will see that Abaqus, for the buckling problem particularly, is actually iterating to try to get to the final answer. It's doing this. It's applying Newton-Raphson procedure, Newton's method, this is called Newton's method, by the way, to solve this equation. Now, this is a single equation, right? For multiple variables, we have to get a little bit fancy, right? So my residual now depends on deflections. So, right, so, sorry, it depends on a bunch of equations I have. How many equations I have? You have 1,000,000 degrees of freedom. Huh? I have 1,000,000. So I'll have 1,000,000 equations. So I'll have a vector of residual forces, or residuals, right? That's basically that. One thing that I actually forgot to point out, when you're using Newton-Raphson procedure, you're actually trying to find equilibrium state. Because isn't this a load applied, 8? Well, it was 16, but this is basically your forcing function right here, right? And so I'm trying to find the internal forces in the body that actually make this equal to 0. So in fact, when you're actually solving Newton's method, you're trying to find equilibrium. And that's what Abaqus tells you: equilibrium iteration 1, equilibrium iteration 2, 3, if you look at the message file. It's because you're actually trying to solve to get equilibrium, so that the internal forces in the body equilibrate the external force applied of 16 pounds. Okay? And the solution for this problem is that U needs to be 2, equal to 2, to get it to equilibrate the external force. Does that make sense?
Yeah, so, for example, in Abaqus, where does bring the initial guess for you?
It's going to use 0 as an initial guess. And then it's going to, as you apply it, you're going to increase the load slowly. Then it's going to calculate what the new U is as you move forward in time.
So whatever initial guess you choose to get for the answer.
Abaqus is going to start with 0. U equals 0. No displacements. Unless you have a previous step where you apply a static load that is going to start from that displacement that you started as your initial guess moving forward. Excellent. So now let's go to 1,000,000 degrees of freedom. So I have 1,000,000 equations. You'll have to do perform Taylor series expansion, same procedure actually. But now you have 1,000,000 of this, and you have to do now the gradient of R. And the gradient of R, I'm sorry guys, but I have to tell you that the name of the gradient of R in this method is called Jacobian too. Okay, so don't confuse this Jacobian with the Jacobian from isoparametric formulation. Is not the same. So it's the derivative of R with respect to each of the displacements. You have to calculate this matrix, which is fairly large. You have to calculate this. It will be 1,000,000 by 1,000,000, okay, in this example. And you'll have to then calculate the, so do you agree that the future, I want the residual to be 0? Right? So then I have to solve for this delta U. And so then I have to take this to the other side of the equation, invert this. And so that's why I have this equation to correct the deflection. So U nu is U old plus a correction du, which is based on that formula. And so that's what I get there. Okay? So that's the correction. You guys have any questions on this? No questions on this? An example works really well. 2 equations, 2 unknowns, nonlinear. And so I want to solve for U1 and U2. Of course, the solutions will be can be found when these two curves, so if I plot this and I plot this, where these two curves intersect is the solution. So we can actually solve this graphically and check our solution, isn't it? So now what I want you to think about here, I want to think about this. You have 1 million equations, right? 1 million unknowns. So somehow these 1 million equations, if you could plot it in the nth dimensional space, these are all somehow at some point they're going to intersect at one single point. Okay? Right? To give you the solution for the problem. However, there is a potential. There's a potential that in a nonlinear problem you have multiple solutions. Because don't you agree that sometimes you can have two equations that intersect each other multiple times? So you could have multiple solutions to a nonlinear problem. So keep that in mind. Okay, so you can find the gradient of R really quickly, which is derivative of R respect to U1. You guys can try that. So derivative of R respect to U1, R1 respect to U1 is minus 4 U1. There you go. No, shoot. No, there you go. That's correct. Right? And then derivative of R1 respect to U2, is that right? Yep. And then so forth. You guys can check that. Okay? And so once you calculate this gradient, right, you have this gradient. Tell me if I'm right or not. I already have this, don't I? I have to just invert it to get this. And R bold U is easy. It's a vector, which is evaluated at U old. Once I have this multiplication, I correct it to U old by adding to U old, and I'll get U new. Okay? I actually did that in Excel. I don't want to confuse you too much, but I took the value of X. Now I'm using X's here instead of U1 and U2. Pardon me about that. But by the time I was done, it was too late. I couldn't. It would be taking me too long. But anytime you see X, just pretend it's U1. So U1 old, U2 old. I made it 0.5 and 1 just for fun. And so then I can calculate my vector R1 and R2. Okay, so instead of F, I also messed up. It's R1 and R2. I can get that. Then I can calculate Jacobian and the inverse of the Jacobian. And then I can get dx as J inverse times F, that column F. And so if I take this dx, this du, basically, this vector, and correct the guess that I had, I'll get the new pair for displacements, U1 and U2. Then I can use this as my new guess, and I can continue this all the way down. You can see here how I'm actually, it's basically approaching a dx of almost 0. So I start with a large dx, and these dx's are fairly 0, which means I'm approaching the right solution, the correct solution. So it took me about 3 iterations to get there. And so you can see that I actually got it right. Here is the plot for one of the equations, and here's a plot for the other equation. It intersects here and here, and my solution here matches the intersection here. Okay, really, really well. Okay, so that's nonlinear Newton-Raphson procedure for you in one-on-one course on that, really quick. Is there any questions? I'm willing to go back and kind of go slower if you want in any of this stuff.
Yeah, so as you said, there's multiple solutions sometimes. Is where you begin your guess going to...
Yeah, so where you begin your guess. If I have begun my guess about here, I think I'll have approached that solution instead of the other one. So what the lesson learned here is that you're going to converge to an equilibrium state that's closest to the guess that you had, because you're basically looking at a search of the solution near that vicinity. Is there a question? Great. Here's a more general 3D nonlinear formulation without going into the details and driving you nuts about it. But strain equals B times Q, we covered that before. Say stress is a function of strain in a nonlinear manner. Basically, your residual is going to look like this. It comes from the weak form straight. I have not substituted what sigma bold is. Normally, sigma bold is what? stiffness D times strain, and strain is B times displacement. So I'll get BdB, right? But here, because stress depends on strain, and strain depends on displacements non-linearly, I haven't substituted what stress is. But you can see here that the equations are basically the same. And now I can use Newton-Raphson procedure on this. That's my R now. And so when I use R, I can now use the same procedure I have here, showing you here, to solve that 3D finite element formulation. In a very simple manner, I'm really trying to. And here's an example of a rubber bar. Stress is a function of strain in a very strange manner, by the way. This is the curve for that. You guys can go and examine this example if you want. It's not very different from this example. I just chose a different equation. Okay. But if you went through that example, you'll get a Newton-Raphson equation fairly quick. Okay, let's cover one more topic, the final topic of this course, fraction mechanics. So we'll hit that too. Before I continue, give me 1 minute. So one more topic, fraction mechanics. I don't have to even explain why we need to look at fraction mechanics. If you have a flaw and you apply loads and the flaw is large enough, trust me, I think I have about 10 examples here, and that's not even complete. If you have a flaw and it's large enough and you apply loads, there's a flaw at which that crack will propagate and will result in failure. So it's important for us to also pay attention to that. So fracture is basically a creation of new surfaces within a body. And so usually the fracture process starts with nucleation of the crack. So it nucleates and then it coalesces into a larger crack, and it can propagate from there. Okay? And in the flaw, if the flaw or the defect is large enough, then under the loading conditions, it will propagate to failure. Fracture can be either ductile or brittle. Today we're going to be discussing fracture propagation where the crack tip does not experience, it has a small plastic zone, but it's not significant compared to the far field, which is mostly linear in nature. Okay, so we're not going to cover elastic plastic fracture mechanics here. I don't think we can do that in less than 16 minutes. Okay, so we're not doing that. But this should be sufficient for a lot of your problems that you'll encounter in real life. There are 3 types of mode of fractures, mode 1, 2, and 3. We'll be focusing on mode 1. In a lot of cases in real life, you can actually turn a lot of your problems into mode 1 analysis. And so that's why I'll focus on mode 1. So there's ways to formulate your problem in a way that's a mode 1 problem. So for example, if I have a crack tip that's slanted, what I could do is maybe look at the max principal stress or the stress that will open that crack and perhaps follow that instead. But that is a much complex subject. So for now, we're going to focus on mode 1 crack propagation, okay, for the time being. Okay, so this is not actually a very difficult idea, you know. So what we're talking about here, do you agree that when you propagate a crack, new surfaces will form? Yeah? you agree that if I apply a load to this pen and I put a crack in there, you agree that the stiffness will lower? Does that make sense to you? If I put a crack there, so there's no crack, I load it up, it's fairly stiff. If I put a crack right through the center, it should be less stiff, right? So did I have loss of strain energy because of this? So when you form a crack, when there's a crack that forms in the structure, there's creation of new surfaces. And this creation of new surfaces causes a loss in energy, strain energy, okay? And that loss in strain energy is called the energy release rate, okay? So the energy release rate is a change in strain energy due to increased area of crack propagation, okay? If this G, if this value of G is greater than the critical value, which is a material parameter that can be measured in a test, then the crack will propagate. But if G is the energy release rate is less than the critical energy release rate, then the crack will be stable. It will not propagate. Another measure of crack propagation is stress intensity factor. And so stress intensity factor is, in essence, if there's a crack in the structure, the stress at the crack tip will be infinite. Stress intensity factor provides you a mean of measuring that stress intensity, basically looking at the field surrounding the crack tip. And so K usually takes this form. K is equal to F times sigma square root of pi times A. F is a material geometry typically, geometry and loading dependent. Stress is usually the far field stress. Pi, you guys know what pi is, hopefully. 3.14159. I will not continue from there. And then A is a crack length, okay? It has units of MPa square root of M. So pressure, units of stress, square root of length. The fracture toughness of the material can be measured. This fracture toughness is measured using the ASTM standard E3999. So it's a material property that can be measured for steel, aluminum, whatever you're working on. You can measure this property. Okay, and now what you can do is convert this Kc, this fracture toughness, you can convert it to G to get the critical energy release rate. So if I know K, I can take the square root of that divided by the modulus, and that will give me G, the critical energy release rate. So step 1, do the test. ASTM standard E3999. E399. And that will give you the fracture toughness of the material. Then take the fracture toughness, square it, divided by the modulus, and the modulus will depend if it's plane stress or plane strain. You will have to adjust it accordingly. And that will give you the critical energy release rate. And so once you have the critical energy release rate, you can now compare this to G. Now, how we calculate G? You can calculate G using Abaqus. And you can calculate G using 3 different ways. There's actually 5 different ways. But I will show you 2 different ways here. And hopefully we can make the other way work, okay? The process is fairly simple. The strain energy on the applied loads, we've already covered this. The strain energy is basically the deflections of the whole system transpose times the whole stiffness matrix of your finite element times Q minus Q transpose F. Now, Abaqus actually gives you this value for the whole model. It can plot that for you. In fact, for your buckling model, I encourage you to plot the strain energy. You can actually plot that. And when a strain energy becomes not quadratic, so it's supposed to be quadratic. Doesn't this look quadratic to you in nature? So it should look quadratic, and then when it's not quadratic anymore, that's when buckling is starting to occur. So you can actually use that as a measure as well. Not just the other. I showed you some other ways in the previous lecture, but you can also use strain energy. So strain energy can also be calculated in the problems that you actually solved in class. Once you have the deflection, you know the stiffness matrix of the whole system, this is fairly easy to calculate. So if I know u, then I can calculate the derivative of u with respect to the crack length. And so when I take that derivative, which is fairly long here, you will see that if for the same force, the crack grows, then the force did not change, you agree? So the derivative of f with respect to crack length growth is 0, so this rate is 0. That's this derivative, that goes away. When you take some of these derivatives, you'll find that you get a kq minus f. This is 0 by equilibrium conditions. Okay? So you can calculate g just by simply calculating this right here. Minus 1/2 q transpose, change in stiffness divided by change in crack length or crack area times q. And if you calculate this, you get g. That's one method. Another method is actually even simpler. You run Abaqus, get the total energy for the crack length you put in there. Then run Abaqus again, but now increase the crack length just a little bit. And let Abaqus give you the total energy. So you have now the strain energy with the original crack length you had in there. You get the strain energy with a little bit longer crack length. It will give it to you. Abaqus will give it to you. Calculate the difference between the two models. Do you know how much you extended the crack in the model? Bam, you get G. And these two methods will match each other. The third method is a contour integral that Abaqus has. Abaqus has a way of calculating this using a contour integral. I won't have time to discuss the theory here, but if you look it up online, I think you will learn, or get a book on fracture mechanics, you'll learn how to calculate the contour integral approach. But I showed you two methods. They usually match really well. Once I calculate G for my problem, okay, I compare that with GC, and if G is greater than GC, the crack will grow unstably. If G is less than GC, the crack will not grow. Now, that's true for a single static loading condition, but if you have fatigue loading, you will use this G in the loading spectrum to determine whether the crack will propagate due to fatigue conditions. And then you will have to use Paris law, and so that will be out of scope for this class, but if you want to learn some more, I can send you some good books to look into so you can purchase. Okay? All right, so with that said, this concludes Finite Elements 168. So we appreciate, Leonardo and I appreciate